So this next piece here in chapter 8 is on vectors. So you guys that have had physics, be a lot of overlap with this type of stuff. You've been exposed to them before. You guys that haven't, this lesson today is going to be a lot of the legwork, a lot of the definitions, a lot of the basic properties of vectors, and then tomorrow we'll use those for applications and story problems and all that stuff. So there's a lot of definitions, there's a lot more notes than we typically do in this class. So what I will do is also post PDF version of these. If you guys want to print them out and have them to reference through instead of writing everything down, you're welcome to do that. Or if you do want to write them down, if that's a way to help you remember them, then great. So this little link up here is just kind of, it's a website that'll tells you why we use vectors. It'll go through some of the properties and stuff with them. The physics is the big application with them. Tons of applications to airplane problems and things like that. Okay, so a few definitions here to start. So vector is a quantity that has a magnitude and a direction. You can basically think of it as kind of like a line in space as well, or the two ways you want to think about these. Okay, vectors are represented by arrows, so we're not just doing lines anymore. We're showing a magnitude and a direction. Okay, the length is the magnitude. Okay, so in the direction of 45 degrees east, we have a magnitude of 500 miles an hour or whatnot. Okay, and the arrow shows the direction. So those are the two main pieces with it. There's these things called zero vectors. So that guy has a magnitude of 0. Okay, it can go in any direction, but basically has a length of 0. Okay, the only way two vectors are equal is if they have the same magnitude and same direction. So you can have a vector that has length of 10, but if they go different direction, they're not technically equal. Okay, because if you're sending an airplane in a different direction at the same speed, they're doing the same thing, but they're going different places. Okay, so it's the only way they're equal. We use V's and W's a lot with vectors. Okay, here's kind of how we start doing some operations with these. Okay, we want to add them, subtract them, and different things like that. So first thing is here, I got a vector V down here. Point down here represents the initial point, arrow shows the direction. So we could say this length, we could say the direction. Okay, I got vector W up here as well. So it starts at the initial point with the dot and it ends at the arrow. Okay, you always connect these things tip to tail and tip to tail. So if I plot V, I plot W. If I want the sum of these two things, it's this black vector here. So it's going from where we started to where we ended. Okay, so there's V, there's W, there's V plus W. So it takes a little getting used to how we work with these things. Here's a couple more examples. Here's the vector V. Okay, here's 2V. Well, it goes in the same direction. Its magnitude or its length is just twice as long. So this guy here is just 1/2 of 2V. Now in negative V, okay, these guys are interesting. It's staying in the same kind of spot here, but basically the dot and the tail flip places. Okay, so this guy heads in this direction, negative V heads in this direction, but it's kind of taking up the same space. Okay, here's some examples. Here's a vector V, here's a W, here's a U. We put them on a grid so we can actually work with them and we can look at slopes, we can look at directions. Okay, we're going to do three things. V plus W, 2V and a minus W, and 2V minus W. So we're basically going to put this one together here. Okay, so if you want to pause it and kind of think about what these guys are going to look like and see if you can get the vector, that might not be a bad idea. Here's the V plus a W right here. So basically, we're taking the V, we're going to literally move this guy right here tip to tail. So this point is going to this point right here, down 2 and then over 1. So here's the resulting vector here in blue. Okay, down 2 over 1, and that guy comes up that way. Okay, now this here just gets us set for the next problem. Here was a V, so up 3 over 2. So a 2v up 3 over 2, up 3 over 2, and there's where it ends. Same direction, twice the magnitude. Here was an old w. Notice we can kind of move these things around, okay? So as long as we're keeping the same length and direction, we can move them around the grid. So if v was down 2 over 1, or sorry, w, down 2 over 1, so a negative w, it's going to take the same place in space, but these arrows are just going to switch. Okay? Now, if we want to put these together, 2v minus a w, take the 2v you got here, take your negative w. It's always tip to tail. So this little piece here is going to end up right there. And then we're going to go over 1 and up 2. So that little ending point always tip to tail. 2v minus w, the thing we care about here is the one in black. That's 2v minus w. Okay, from starting point to ending point. That's the only place you're going to have two tails pointing at each other. Okay, everything else is tip to tail. Okay, we'll do that tomorrow together in class to start. If you want to look at them and get an idea and some thoughts, go for it. But we'll start class with those tomorrow. Okay, magnitude. Here's the notation for it. So it's two lines. Okay, with a vector in here. It could be a v, w, u, whatever. Properties of it. Magnitude's always got to be positive. Okay, you can't walk home in a negative. You can't walk negative 3 miles home. Okay, the direction can or the negative can show you direction, but magnitude always has to be positive. Okay, we have to cover positive distances, positive lengths. The only way the magnitude can be 0 is if the vector is 0. Okay, that just kind of makes sense. This guy here, now we got a little alpha. Okay, we're so used to thinking that with angles and whatnot, and there's only so many letters, so many Greek things to do. So this little, think of it like a little a, basically. Okay, the a is just going to be some scalar. So if I want the magnitude of, like, let's say 2v, okay, I can separate the 2 and kind of pull that out front and then find the magnitude of v. Okay, so scalar just means a number here. All right, how we write these things algebraically. Okay, it's going to take two different forms, and I don't care which form you write these in. It's whatever's most comfortable to you. So you guys have done physics. Hopefully this overlaps. So we don't write it with parentheses. Okay, we write it with the little, little alligators, the little Pac-Man guys here. Okay, so that's going to show us it's a vector. So a and b are real numbers, okay, and it's called the components of the vector. Okay, so you would see something like 4, 7. Okay, these symbols are going to show me it's a vector. Those are going to tell me the components. Okay, here's kind of what we're doing with that algebraic thing. So we have a point AB. So this guy is what, 2, 4, 5. So this guy is 5, 5. Okay. So if we want to use a vector to get to that point in space, we're going to say the vector equals 5, 5. Okay. So I'm going to use a vector to get to that point. But notice the difference between this notation and our vector notation. Okay, vector's got the little the sideways V's. Okay, position vectors. Okay, so these are going to be useful when we're doing story problems, how we show where vectors are and whatnot. You can think of it exactly like slope. Okay, here's how you find it. x2 minus x1, comma, y2 minus y1. Okay, slope is obviously those two numbers divided, but there's your position vector. Now the nice thing with these is they will tell you which one's vector 1, which one's vector 2. So unlike slope where you got to pick and they were interchangeable, the vectors will be set. Second minus the first, comma, second minus the first. That'll tell us the position vector. Okay, so we'll see you guys in part 2 and we'll keep going.